Good morning or good afternoon, depends on your location. First, I'd like to thank you very much for being here. It's a second session of this webinar, but still we have a great number of participants. There's a nice feeling, thank you for that. My name is András Szigeti, I'm the CEO of Technorglenda Hungary. I will be your main presenter today. And the reason why we decided to organize such an event and give a broad picture about this unique technique of ion milling, of sample preparation, is because time to time we realized that most of the scientists and the laboratories are focusing on the observation part only. They're purchasing brilliant and very nice microscopes, which are very useful. But there is a missing part, namely the high-quality sample preparation, and that's equally important to have an ultimate result from the bark material, so you cannot skip any part of this workflow. So we would like to show you all the possibilities of the ion milling technology, but before that, we'll cover some historical part as well. The other reason of this webinar is that our company is celebrating the 30th anniversary this year, so it's a good timing to see where we came from, what we have now, and which are the directions where we can go for the future. My presentation will take about 40-45 minutes roughly, and then we will have a short Q&A section where we have the possibility to pick some questions and answer them publicly. But in the meantime, please feel free to use the chat option. And during the presentation, you can raise your questions and my colleagues will do their best to answer them. Don't worry if your questions are not answered here, because we had no time for that. After the webinar, you will receive a follow-up email, and in that email you will have the recording of the webinar, so you will have the chance to review it anytime or distribute it if you want. And also you will receive the whole list of questions and the proper answers for those. As I mentioned, we will start with a historical part of the presentation, just see how this technology was invented, what kind of demands brought this to life. Also, we will check some milestones which gave significant advantages or significant steps to the possibilities, and we will see and look through the main players at this moment on this specific market. Then we will cover all the approaches and the applications where this technology can be used, and also I'd like to show you some special cases just to prove how broad the field and the applications and the cases where you can use this technology with great success. At the very end of the presentation, we will spend some minutes just to see what kind of ways, what kind of steps can help to solve the future problems, which are the directions where we should go together. But in front, I'd like to tell you that it's not just about us, and it's not only our decision, but we need a specific information for seeing those paths and directions, how to help you in the future. So, the past. In the center of last century, where the story begins, actually, in that time, the area of interest was moved from the macro structures into the micro and later the nano world. So microscopies, and especially the electron microscopes, became the main tools for the evaluation, and these microscopes, these electron microscopes, they gave the chance to evaluate and observe the nanostructures, but that time, the sample preparation was not equipped and not developed enough to produce amorphous and damage-free samples, and that was a very weak point at that time. So something was needed, definitely. All the methods what were used at that time, like mechanical polishment or chemical etching or so on, after these steps, a significant amorphous and damaged layer remained on the samples, and a new technique was needed to remove those layers. Because what we have usually is a sample, a valuable original structure, and on top of that we have a thin amorphous layer where you have you can easily lose all the signals. Usually, and on the screen you see that usually we use the EBSD technology just to evaluate the quality of the surface, because it's a very sensitive technology. So a very thin layer gives you the information only, and if it's damaged or amorphous, you don't have any kind of signal. So if you see the amorphous layer on the top, basically it's useless, so it's definitely something you need to remove. Of course, the finest steps of mechanical preparation or other techniques can remove a part of it, but still some amorphous will remain on the surface. The bigger problem is that below this surface there will be a crystallic structure where you can get some information, but it's very important to understand that usually this structure is deformed, destroyed. The orientation of the crystals were changed. So actually this can lead you to a very dangerous point, and you may think that what you see is the reality, the original structure, what you're looking for, but it's not, it's definitely not. So that layer must be removed somehow, and here the mechanical polishing is just not enough, or any kind of technique what you may use. So you see that if you reach the region where you have the original properties of the sample, it looks totally different. So in the late 70s and early 80s, a new possibility came, named ion beam milling. Actually, that was a great idea, and was a very, very important and useful step made by our noble competitor, Gatan. Gatan is an American brand, and their first ion mill was the first and only one at that time, I would say, the duo mill. What helped the scientists with this new possibility, and it helped to remove a part of this amorphous or destroyed layer. The idea was great, and it was a really significant step, but there were some limitations, what needed to be upgraded, needed to be solved. For example, the samples were stationary, and that was actually a bigger problem than it seems to be, because moving the sample can help to avoid many artifacts what you may see on the surface. Also, the angle of the treatment was fixed around 15 or 20 degrees, and actually the ion source was a great tool that time, but the energy range where you could adjust the accelerating voltage was really narrow. So basically it was capable for the bombarding of the sample with the high energy argon ions. And the high energy ion milling causes also some damage on the layer. So something was needed. And in that time, a Hungarian team came from the Academy of Sciences, Hungary, and also some researchers from the Technorg GmbH, was the pre-company of Technorg Linda. And this scientific group invented some new technology and new tricks what helped a lot to reach the desired level of these samples. The first step was a new ion source. It was the first electrostatic ion source, and it's operated between 2 kilo electron volt and 10 kilo electron volt. Basically, the whole range was very useful, and from that time you had the possibility to go a little bit to the lower range of energy and have a little bit smoother surface. But another step was helped a lot. Again, this was the low angle treatment. As I mentioned before, this time that angle was fixed and too high, way too high for a high quality treatment. But these scientists figured out that the optimum angle in most of the cases is somewhere between 6 and 8 degrees. In delicate unique cases, it can be much less, like 3 or even close to 0. But in the new machine you see on the picture, this possibility was available, and you could choose the right angle for your samples. Actually, the lower the angle, the smaller the damage is what you cause on the surface. And the third one is the sample motion, including the tilting. So I mentioned that you could tilt the sample holder and adjust the angle between the sample and the ion beam. But also they started to rotate and later oscillate these samples, what helped a lot to avoid a lot of artifacts on the samples. Still, the high energy treatment, as I mentioned, cannot clean all the amorphous and all the damaged layers, because high energy atoms, even if you turn down the energy around 5 or 2 keV, these high energy atoms make some damage on the surface, so something is needed to clean those samples further. And in 1996, a new invention came, the first low energy, the first dedicated low energy ion source on the market, from the team of Technorg Linda, Hungary. That ion source operated below 2 keV, and in high vacuum circumstances, even the 20 or 30 electron volts can be used, for example in Auger systems. But in normal mid-vacuum, usually we go down until 100, 200 electron volts. But it's a great tool for cleaning those amorphous and damaged layers caused by any previous steps of preparation, including the high energy ion bombardment. And you can see on this on the screen what's the difference between the high energy and the low energy steps. And thanks to this new ion source, in 1999, the Berkeley University of California, there was a sample, a silicon monocrystal sample that was prepared by the scientific group of Berkeley. That was the first amorphously atomic resolution image was made ever in the world. So I would say this new possibility, the low energy ion source, opened the door of the world of atomic structures, and from that point the scientific community had the possibility to see these atomic structures, not just imagine how they should be and should look. So I would say that was a great milestone, and definitely a very, very big step. The IB4 was the first machine what contained the low energy and the high energy gone together. So basically that was the first device that could cover the whole range of this preparation line, from the very first step until the finishing cleaning. Another great step was, and invention was, the gentle mill. It was a purpose-made machine for final cleaning the pre-prepared TEM samples, or the final cleaning the FIB lamellas. Actually, the biggest point was here that the gentle mill was the first device what was computer controlled, and here you could find the capability and the possibility for using recipes. And if you think how important was that step to replace the human power and programming the machine to do the whole job, you can understand how significant was this step. Actually, the gentle mill device was really popular for many years. This is the first generation, what you see on the screen. Now we have the third one, and we sold much more than 100 pieces only to Japan, and only for final cleaning the FIB lamellae. This was a great purpose-made tool, and it still is. So you can improve your lamellas easily with such a device. All right, let's take a look to the major players today. As I mentioned, a US brand, Getan, was the first who invented this technology, and they made the first device in practice in the late 70s and the early 80s. And from the 80s, Techno Orglinda and that scientific group came and made very serious steps to make this technology really useful in practice. From the early 90s, we had another company called Balzers, who purchased and bought the license for using the technology, the ion source of Techno Orglinda. Then they reorganized this technology to another company called Baltec, and Baltec was acquired by Leica in 2007-2008, and from that point Leica is one of the major players on the market. Actually, that technology was based on the license of Techno-Org. We have another US brand, Fisciona Instruments. They also have a great portfolio for ion mills and different kind of sample preparation devices. And for many years, that was a quite stable market. And from the late 2000s, 2010, two Japanese brands made their own technology, their own ion milling devices, mainly for the SCM sample preparation part, namely Joule and Hitachi. Actually, before 2010, Hitachi distributed our gentle mills in Japan and that area, that region. But after 2010, they launched their own technology, and from that point, they sell ion mills by their own. As you saw, most of the players have a quite great portfolio. I mean, hundreds or even thousands of different technologies, different devices. And only Techno Orglinda is still with a dedicated company only for this technology and this solution. So our portfolio is focused and containing only the ion milling technology and some additional mechanical steps and tools for helping this workflow. And also we spend our time and energy only to develop this portfolio, this technology. So we definitely have a deep understanding and experiences of more than 3 decades. So we strongly believe that this is the main reason why we can develop those steps. What gives you newer and newer possibilities and newer solutions before anybody else. Also, being a small and dedicated company means we have the flexibility. So in case our customers have some kind of unique needs or demands, we are open and capable to modify and customize our solutions in order to meet with those special needs. Right, we're here, we are in the present. Let's see what kind of possibilities we can offer, or this kind of technology can offer to the users. The main part of the technology is the same, even if you want to use it for TEM or SEM applications, but the design of some parts are totally different and optimized for those purposes where you want to use them. So that's why we have a dedicated product line for the SCM and EBSD samples. We have other tools for the TEM preparation, and also we have purpose-made machines for cleaning, final cleaning the FIB lamellas. Let's see the SCM field first. We can choose from two different approaches. One is the surface polishing, when you want to clean the original surface of the sample. Here you use a shallow angle usually between 3 and 7 degrees. And because of the shallow angle, the beam will be elongated on the surface, and during the rotation of the sample, you can reach a relatively large area what will be cleaned in the highest level. That ultimate quality area can be around 1 square centimeter or even larger. We designed different type of sample holders in order to meet with the needs of different applications. Sometimes you have large samples what you want to prepare. Here you can use the flat head type sample holder, or there is a standard type one where you can use your pin mounts from the SCM, the small or even the large standard of the pin mount holders. And also we have a specially designed sample holders for the samples are embedded in resin. The other approach, the next one is the slope cut or the cross-sectioning. Here you have a tilted sample and you cover one part of the sample with a mask. In our case, it's a titanium mask, and just next to the mask you will cut into the sample and make a new surface what is absolutely ready for any kind of observation. Here we offer 30, 45 and 90 degree sample holders. All of them has advantages and also disadvantages. It's up to you which sample holder you want to use. Usually we offer the 30 degree sample holder for bulk materials where it's not important the exact place where you want to cut the sample. The 90 degree has other advantages. It makes a real slope, a real cross section, and also in case of heat sensitive samples it can be add some other advantages as well. In case of the conventional transmission electron microscopy sample preparation, usually we have a small piece of the material what is should be encapsulated in a titanium grid. This is the way how we do it. And then together with these titanium discs, you can polish it mechanically until a certain point. Then you can choose between single or double-sided sample holders. Depends on your aim. The single-sided holder gives you more chance for lowering the angle until almost zero. in some dedicated and delicate cases it can be needed. The double-sided gives you the chance to use the recipe-based operation mode in the machine, and the whole procedure can be done by the computer, because both sides of the sample should be treated. So in case of the single-sided holder, you need to flip it over by your hand. The double-sided holder can turn over automatically. And after a good preparation, you can reach the ultimate result without any kind of damaged or amorphous layer. This is one way. The other one, maybe nowadays this is the more popular one, using a focused ion beam, a FIB, for cutting out a lamella, and then you clean that lamella and remove the last part of the amorphous. Usually users, our operators using OmniProbe grids to fix the sample, to fix the lamella, what can be put into our sample holders. And using the low energy argon ions, you can remove all the amorphous layers. Usually you have some nanometers or some tenths of nanometers around the lamella everywhere. Here you can see the edge, but also this amorphous layer is on the surface here as well. So you need to remove from everywhere in order to see the original structure. Also the gallium implantation or other unwanted artifacts can be removed and cleaned within several minutes. And this is the final solution, what you are looking for. These are the approaches and the possibilities, but let's take a look to the typical applications. Actually, there are many, so we will choose some, just give you a picture what kind of usage can be real. Actually, metallurgy is one of the major applications. Any kind of metals, including the soft and the hard types, can be easily prepared with argon ions. Here you can see an aluminum sheets, but iron or even the titanium can be prepared easily, especially if you choose the right configuration of the machine, because we have a dedicated ultra high energy ion source what can speed up the cutting in case of really hard materials like titanium. From the mining industry, we have a beautiful sample here. It's a natural diamond. It's obviously very hard to prepare mechanically. Here you see first they tried to use a mechanical preparation, the mechanical polishing, including the finest steps of that approach. And then they tried also a chemical etching, but combining those techniques, that was the final result, what they could achieve. About the half of the points were just not good enough for indexation. So that's a very poor result. But after some minutes of ion milling, actually 100% of the area was indexed. Actually, you see 3% of zero indexing here. That's because there are holes in the sample. So where you have no material, you have no signal, obviously, but all the other parts were indexed, including every single area of that sample. Some other samples from the electronics. This is an LED cross-section. Here you can see a multi-layer part, probably it's a mirror. This was the area of interest, but after mechanical polishing, that was the finest result they could achieve. So they tried some minutes, it was 10 or 12 minutes of preparation by the ion beam, and that was the result. That was the difference between the two results. It's quite obvious. Even the smallest details can be measured. Here you see. A nice example from the territory of geology. Actually, geologists have great and very tricky samples usually. We really like them because this is an area where we need to find out some new tricks and new approaches. It's a great feeling when we can solve these problems. Clay is definitely a very difficult sample. It's easy to imagine when you try to polish it mechanically how you will mix all the structures and all the parts and smash the whole thing. Cutting this clay sample with argon ions, it's probably the only way to open the inner part and see the original structure of it. Another delicate sample from the application of material science is a special metal foam containing copper and nickel and other alloys. Really sensitive structure, so it's quite easy to destroy it if you use any kind of mechanical treatment. But by cutting it by argon ions gives you a absolutely great and ready for any kind of observation quality. Other applications, when you have very hard materials, you saw the diamond, but it can be tungsten carbide or other ceramic samples. It's a real challenge to prepare these samples with any kind of techniques and technologies. But using the argon ion milling, it's a quite easy task, I would say. And you can see all the details, including the very first layers of it. Right, you see that even if you have soft or hard materials, including the delicate samples like metallic foams or other cases, the argon ion milling is a material independent and very easy to use solution for those. But there are some special cases where you need some tricks. For example, if you have really hard and very soft materials together, like tungsten carbide and cobalt in the same time. In case of any kind of polishing, including the mechanical polishing or polishing the surface by argon ions, it's very easy to polish out all the soft parts before even you touch the hard areas. So something is needed to have a real useful sample. So in these cases, the only good approach, the only possibility what you have is making a slope cut, because in that case the preparation will be done under 0 degree. So the soft and the hard parts will be cut in the very same time. So if you see the new surface, you can observe all the points, all the parts in the same time without any kind of artifacts or remained damaged layers. It's a very similar case if you have a porous material like limestone in our case. Actually, it can be avoided to have such a rough surface if it's needed. But in many cases, for example, in case of EBSD, you don't need to have a flat surface. You need to have a clean surface, but it's different. There are some tricks to make this leading edge more even, but we wanted to show you that even if you have that kind of rough surface, it can be clean enough to make a brilliant and clean EBSD image or any kind of observation. there are some samples which are really heat sensitive, and it gives you another challenge, another problem to solve, because obviously you have different possibilities to cool down the sample. If it's really heat sensitive, usually use an effective liquid nitrogen cooling option, what can transfer the heat from the sample. That's great. But if your sample is not heat conductive, it's really difficult. Even if you have a very efficient cooling system, it's almost impossible to transfer the heat away from that point it was generated, namely the point where you hit the sample with the ion beam. So it's not enough. You need to do something else. For example, turning down the energy and reduce the heat load. But in that case, you will lose time. The preparation will be much longer. So that's why we figured out some tricks, and also we have a very special design, the sample holder, where we can keep the high milling rate and in the same time protect those heat sensitive samples. But this is a topic of another webinar, because the main reason and the main goal of the webinar today, just to give you the whole picture and to show you how useful this technology can be. And later on in the next several months we will have dedicated topic-oriented webinars, including the heat-sensitive sample preparation, but we'll also have a presentation about the fib lamella cleaning and other areas. So here, I'd like to show you that even in the very heat-sensitive cases, there is a solution. Here you see a balsa wood, but it's a very delicate sample. It has a special inner structure, and thanks to this structure, the balsa wood is very light but extremely strong in the same time. And this inner structure can be observed only if you have the right approach and the right recipe, and also the right devices how to make it, because it's absolutely easy to destroy it or burn the whole area. The laminated paper is very similar, but you can see that the great result is achievable. In other cases, you want to protect your samples. For example, when you have something that can be sensitive for oxidation. In these cases, you can use our VTU technology. The VTU means vacuum transfer unit. So the prepared sample can be transferred to the glove box, or in some cases directly to the microscopes by using our VTUs, and close it into the capsule and avoid any kind of oxidation. It's up to you. You can use vacuum or any kind of protective gases. Usually we use argon, but it can be dry nitrogen or anything else what you are choosing. Just to show you the difference between using or not using the VTU, there was a zinc alloy sample prepared by the group of CSIRO in Australia. Once they prepared it, but during the transportation they did not use the vacuum transfer unit. You can see the oxygen peak here. Next time they prepared the same sample, but the transfer was done by using the VTU, and you can see there was no additional oxygen and there was no oxide layer on the surface. Also, you can avoid carbon contamination or any kind of unwanted material on the surface. So again, there are many options. it depends on your special needs and your applications, but you can easily choose the right configuration, what can help the most your day-to-day job, including different type of cooling systems or the different ion sources, because as I mentioned, we have dedicated ion sources for the rapid milling, and also a dedicated tool, a specialized and optimized tool for the low energy cleaning. So you can choose from them. A wide range of sample holders can help your job, and also the recipe-based automated operation mode is available, what can help a lot. The VTU is the last option we just covered. Okay, so this is what the technology and our portfolio has right now, but what can be the future? Because what we see right now, how we see this, that the trained human power is more and more expensive and more useful, and it's a good way. We're happy to see that. But what it means is all the job, what can be done by the computer, by a device, it should be done by that device. So an automated operation mode and a recipe-based operation mode it can help a lot in the day-to-day work. So that's why we already have this option in our machines. But also the remote control is another thing. Especially the COVID has shown us that how important to have such a device or technology what can be controlled from your home or a different location, because during the pandemic or any kind of troubled times, your research or your job will stop if you don't have these kind of possibilities. Having an automated or remotely controlled device is one thing, but a support, an application or service support is equally important. And in these days, especially in the future, probably the online support is getting more and more useful or absolutely key in the life of researchers. So that's why we made strong steps to have an ultimate online support, including trainings, including application sessions, or any kind of help what you need is available right now online. But this is what needs to be developed more and more, because that can help your future job as well. How can we make the life easier furthermore? One direction is combining some technologies and some steps, because usually there are different kind of methods you need to use for reaching the ultimate result from the bulk material, including some mechanical treatments such as cutting or polishing. Also it can be the ion milling, it can be plasma cleaning or coating, anything. And the very last is the observation part, where you use your microscopes or another special devices. So making a combination of these technologies can help a lot, and this can be one way to serve you better, and not just because it makes the whole workflow easier, but also safer. If you see that every single time when you need to change a sample holder or you need to adjust something, you have the chance to break or lose your samples, sometimes after hours of preparation, and this is something what you really don't want to see time to time. So combining these technologies means a much safer solution, definitely. And what else? Actually, we don't know yet. And here I would call you for a two-way communication, because all the willingness and all the efforts from the developers or the manufacturer, it's one thing. We do our best to develop this technology and all the steps, all the tricks to help your job, but we need the information, what is missing or what can help you the most, and it can be implemented probably in these machines, or we can focus our efforts to the direction where you see the most values what you could receive. So please, when you see a survey in the follow-up email, take those minutes. It's a very short one, but please take those minutes to fill it out and send it back to us, because that helps us a lot to meet with your special needs. Actually, in this time and in the future also, we're absolutely open to develop special solutions. You see on the screen, we are open to customize our devices if it's needed, in case of having very special dedicated needs for a certain research. Approach us, let's have a roundtable discussion. We need to see what kind of difficulties you have and what is missing from the current portfolio. We are more than happy to make an evaluation and to see if we can do some further steps to meet with your expectations. So here we have, you will see a follow-up survey. Please use that, and also if any of you are open to go deeply into the day-to-day problems or any kind of needs you may describe us, it could help a lot, and who knows, in the near future maybe we can have some special solutions dedicated to your special needs. Thank you very much. That was the presentation, and now we have several minutes to choose and pick some of the questions you raised and answer them publicly. So let's see the first question here. Can we have detailed information about the lithium-ion battery preparation? That's a good question. Yes, definitely. For today, I wanted to give you a broad picture about the possibilities. But in the next several months, we are planning to organize dedicated webinars with deep content. One of those would be the lithium-ion battery preparation. Also, we would like to give a presentation about the fib lamella cleaning, about the heat-sensitive samples. So yes, definitely, you can have and you can receive real detailed information from us about that. It's a very deep topic, and that application has really special needs. So it's not something what I can answer now. Please join the later webinar. And you will receive all the necessary information what you need. Also, I would suggest to use the survey and let us know what kind of topics you would be interested, because we can organize our later webinars, future webinars accordingly. The next question is, do you have application-specific sample holders, or the user should decide which they use? I would say we don't have dedicated holders for each application, but we have different types, and all the applications have their ideal approach, I would say. So yes, there are some sample holders what can help you and give certain advantages for dedicated applications, but we have great experience in it, so we are here to help you, and we will help you to choose the right sample holder for each cases. The next one is what are the cooling options and what are the sample temperatures with each options during the milling? All right. Actually, we have quite large variety of cooling options, like the Peltier cooling with Peltier elements. Also, we have liquid nitrogen coolings and an automated version of liquid nitrogen cooling. Honestly, it's very difficult to measure the temperature of the sample during the milling, because usually the sample is very tiny. You're in vacuum, so the circumstances are far from ideal. But we managed it. It took a long time, but we managed it, and that's why we have a very detailed database about the exact temperatures in case of different milling energies and different coolings and so on. So we can share the data with you, but I would say the Peltier cooling is good for protecting your samples against overheating, and it can help you to keep the temperature around room temperature. If the sample is more sensitive, you should use the liquid nitrogen option or the automated liquid nitrogen. It's more it's quite useful because it can save you time and energy. And in that case, even if you use the high energy range of ions like 10 keV, the temperature of the sample will be way below 0 Celsius, for sure. What kind of pre-preparation is needed before ion milling? Very useful question. Yes, most of the cases, if the sample allows, we use a high-quality mechanical preparation, mechanical polishing, because it gives you more chance to reach the ultimate result with ion milling. But in some cases, it is just not possible. For example, I showed you the clay sample in my presentation. In those cases, you just use the bulk material and make the cut from the very first point. Actually, that's a topic where we have nice training materials, and also we are organizing dedicated trainings for the mechanical preparation part. How to create a sample what is absolutely ready for the ion milling and give you the most chance for the high quality results. If you are interested, just let us know, and we can distribute and share these materials easily. I have metal wire SEM samples with different diameters from 20 micrometer up to 300 micrometers. Can they be prepared? The short answer is yes. Actually, it's quite easy if you know the right approach. We just prepared such a sample in the last couple of months. If I'm correct, the diameter was about 17.7 micrometer or something like that. It was a platinum and tungsten alloy coated with some kind of polymer, and actually it was quite a routine job. So I will ask my colleagues to send the application note and the results about that. But the answer is yes, it's quite easy to cut these wires. The next question is, you mentioned the high energy ion milling makes some damage on the surface. In case of EBSD, as it is a sensitive sample, the low energy is the solution. In case of SEM samples, almost every case is that the high energy ion milling is enough, because it's gentle enough compared to any kind of other techniques, and you can finish your samples with the high energy. instead of eBSD, that's okay. The low energy makes a real difference in case of TEM samples, where you have a very tiny lamella, and also the amorphous counts doubled twice, because both sizes you have this kind of amorphous or destroyed layers. So it's really critical to remove the last nanometers of these layers, but in case of SEM samples, it's just enough if you finish it with 10 or 8 keV. Next one is no, that was, oh, sorry. Yes, I just checked that our time is over. Actually, we have quite a number of questions, so let us answer it later. And as I mentioned in the follow-up email, all the participants will receive a list of all the questions and the proper answers for the questions. But right now, we just finished the dedicated time for the webinar. So thank you very much for your attention. Please follow us on the LinkedIn and Facebook. You may see some very nice and interesting content on a daily basis. So just follow us on those platforms. And I really hope that we will see you on the future webinars and events. See you next time. Thank you very much.